module in this massive open online course on Bayesian MMSE estimation for wireless communications. So, we are looking at the Lmmse Equalizer for a wireless communication system with inter-symbol interference. Alright, we have derived the Lmmse Equalizer to remove the inter-symbol interference in a wireless channel. Alright. So, now let us look at the error for this MMSE Equalizer. Alright. So, today first thing that we are going to do in this module is the error of Lmmse if we define the error of the Lmmse Equalizer as right expected, remember we have derived the Lmmse Equalizer as x hat of k equals, it is there right above, PD 1 bar 2 transpose H transpose PD H transpose sigma square I inverse y bar of k, okay, correct. And now we want to derive the error for the Lmmse Equalizer, that is expected value of x hat of k minus x of k whole square, which is equal to r, remember xk, okay, we know the expression for the error of the Lmmse estimate, r xk minus r xk y bar k times r y bar k inverse into r y bar k xk, okay, where r xk this is nothing but expected value of, this is nothing but expected value of magnitude xk square, which is equal to PD, that is the power of the data symbols. Alright, r xk is expected value of xk into xk or xk square, which is equal to the power, that is PD. Okay. Now, these quantities we have also derived. Now, r y bar k xk, remember we have derived previously we derived r xk y bar k, r y bar k xk, this quantity r y bar k xk, this is nothing but expected value of y bar k into xk, which is nothing but expected r xk y bar k transpose, and we know r xk y bar k, we have already derived that r xk y bar k is PD 1 bar 2 transpose into H transpose is r xk y bar k transpose of this, which is basically, of course, PD is a scalar times the matrix H, PD is a scalar times the matrix H times the vector 1 bar 2, that is r y k x bar k. Okay. So, therefore, we have expected value of x hat k minus x k whole square, this is the Lmmse equalization error. This is the error of Lmmse equalization. This is equal to r xk PD minus this expression. Look at this, r xk y bar k, r y bar k inverse. This is nothing but the Lmmse equalizer, that is this quantity PD 1 bar 2 transpose H transpose into PD H transpose plus sigma square I inverse. So, this will become minus PD 1 bar 2 transpose H transpose times PDH H transpose plus sigma square I inverse into PD into H into 1 bar 2. This is the expression error of Lmmse equalizer, or rather mean square error. Okay, this is the mean square error of the Lmmse equalizer, that is PD minus PD 1 bar 2 transpose H transpose into PD H transpose plus sigma square I inverse into PD H into 1 bar 2. Okay, so that is the error of the Lmmse equalizers. Okay, so what we have done is basically we have done two things. One is we have derived the Lmmse equalizer and also the corresponding error for the Lmmse equalizer. Now let us do a simple example to understand the application of this concept of Lmmse equalization in a wireless channel with inter-symbol interference. So what we are going to do, we are going to introduce a simple example of Lmmse equalization in wireless channel with ISI. Okay, so let us consider a wireless channel. Let us consider again similarly, consider an L equal to 2 tap wireless channel with Yk equals H0 xk plus H1 xk minus 1 plus Vk. Let H0 be equal to equal to 1, H1 equal to 0.5. So, we are considering a 2 tap wireless channel similar to what we have considered before, that is H0 and H1. These are the 2 taps with H0 equals 1, H1 equals 0.5. Okay. So, H0 and H1, these are the 2 taps. We have Yk substituting H0 equals 1, we have Yk equals 1 times, that is H0 times xk, that is 1 times xk plus H1 times xk minus 1.5 times xk minus 1 plus 2, because 3 dB corresponds to 2. So, this is approximately equal to 4, 2 square, that is 4, this is what we know. Let the noise power sigma square be 0 dB. Additionally, we are also in the noise power, right. Remember, we need the power of the symbols, the noise power, to compute the Lmmse equalizer. So, we are assuming the noise power sigma square to be 0 dB. So, let which implies that ten log to the base 10 sigma square equal to 0, which implies that sigma square equals 10 to the power of 0, which is equal to 1. Now, further consider a 3 tap equalizer. Consider a 3 tap equalizer based on yk plus 2 yk plus 1 comma yk, which is equal to, therefore now writing the equations we have yk plus 1 equals, we have h0 into, or yk plus 2 rather equals h0 into xk plus 2, that is xk plus 2 plus 0.5 into xk plus 1 plus vk plus 2 yk plus 1 equals xk plus 1 plus 0.5 xk plus vk plus 1 and yk plus 3 x, or yk, I am sorry, yk rather equals xk plus 0.5 xk minus 1 plus vk. Now, putting these in a matrix form, putting these three things, stacking this converting this to a matrix form, or converting to vector form, we have the output vector y bar of k. What is the output vector y bar of k? Which is yk plus 2, remember that is yk plus 2 yk plus 1 yk, which is equal to 1.500 01 0.50 001.5. This is our matrix H, this is our matrix y bar k times your matrix xk plus 2 xk plus 1 xk xk minus 1, this is your vector x bar of k plus the vector v bar of k. Remember, v bar of k is vk plus 2 vk plus 1 vk. V bar of k. Okay, so the key thing here to note is that this is your matrix H. This is your matrix H. Let us rewrite the matrix H again. H is basically equal to, the matrix H is equal to 1.500 1.500 Now, the Lmmse equalizer, notice that the Lmmse equalizer is given as x hat of k equals PD into the vector 1 bar 2 transpose H transpose PD H transpose plus sigma square identity inverse into 1 bar k. Let us call this as C bar transpose. So, this can be written as C bar transpose into 1 bar k, where this vector C bar equals, it is clear what is C bar. C bar is PD H transpose plus sigma square identity inverse into PD 1 bar 2 transpose into H transpose, we can call this vector PD, as we can call this vector C bar as the equalizer vector. We can call this vector C bar as the equalizer vector. Okay. So, we are defining this vector C bar, which is the equalizer vector. We can find the equalizer vector, from that we can implement the equalizer, or that is the process of equalization, okay, across the wireless channel. Okay. So, now the key is to compute this C bar, and to compute this C bar you will see that we will need H transpose, need H transpose, and H transpose can be obtained as, now let us write this down, H transpose is 1.50000 or 0, 1.50001.5 into 0 or 1 H transpose. So, this is H, we need to get H transpose. H transpose is the transpose of H, that is 1.500 0.50 which is equal to, let us write it as fractions, 5 by 4, half 0, half 5 by 4, half 0, half 5 by 4. This is your matrix H transpose. Now, we need PD times H transpose. Look at this, this is PD times H transpose, and PD times H transpose is rather 4 into H transpose, which is equal to your 4 times H transpose has been derived above. So, that is 4 times, let us just write this once more for the sake of clarity, 5 by 4, half 0, half 5 by 4, half 0, half 5 by 4 equals 5 to 0 to 5 to 0 to 5. Okay, this is PD times H transpose. Now, we need PD times H transpose plus sigma square I, which is 5 to 0 to 5 to 0 to 5 plus sigma square is, well, sigma square is 1. Remember, we have derived earlier, sigma square is 0 dB, which is equal to 1 times the identity matrix 0 0 0 0 1 0 0 0 1, which is equal to, now if you do this, what we will get is, this is equal to 6 to 0 2 6 2 0 2 6, and this is the matrix your PD times, this is your PD times H transpose plus sigma square identity matrix, sigma square identity matrix inverse. Okay. So, what we have is, basically we have computed until this part, that is PD times H transpose. Now, what we want to do, we want to calculate the inverse. So, this is PD times H transpose plus sigma square I. Now, let us compute the inverse of this matrix. Okay. So, we need to compute the inverse okay, and then we can use this in the computation of the equalizer vector. So, once we compute the inverse, we can use it in the computation of the equalizer vector. Okay. So, what we are going to do is, let us stop this module here, because this is a long example, probably it is slightly tedious to understand all aspects of it in one module. So, let us stop this module here and we will continue with this example, again the same example. We will complete the rest of the derivation, that is derive the equalizer vector as well as the mean squared error of equalization, the mean squared error of equalization of the symbol xk in the subsequent module. Thank you very much.